Some of the hardest problems in the world exist far above the planet. Our job? To launch the smartest solutions, to protect our satellites, clean up our clutter, to propel breakthroughs in propulsion, to learn more about our place in the universe, to outpace emerging threats. Every day, the Aerospace Corporation uses the latest technologies to ensure our nation's safety and leadership in space.
Hi, and welcome to the Space Policy Show. You can find us on Twitter at #the Space Policy Show, and you can engage with us in the Vimeo chat box. Please sign up for the latest news alerts at aerospace.org/policy. Today's episode is really fun. We're talking about space QKD and policy for Muggles with Lori Gordon and Joseph Touch of the Aerospace Corporation. How does quantum work in space? What are the risks? What are current policy thrusts and challenges? What are the next steps in adopting QKD more broadly? The Space Policy Show is pleased to hear from Joseph Touch and Lori Gordon as they discuss technology and policy around these questions and broaden the discussion in their recent CSPS Game Changer publication, Quantum Key Distribution in Space. Lori Gordon is a technology strategist at the Aerospace Corporation specializing in homeland security, cybersecurity, and infrastructure resilience. Lori is also a fellow at the National Security Institute. Joe Touch is a senior scientist at the Aerospace Corporation supporting QKD, P-LEO, and MilSat-ComNet's ground systems, and he has over 170 published papers and 5 U.S. patents. He's an ACM Distinguished Scientist and a senior member of the IEEE and OSA. Over to you, Lori, to get this conversation started.
Thank you, Rebecca. I'm Lori Gordon here with my colleague Joe Touch, and we're excited to talk with you today about quantum key distribution. Why it's important, talk about some of the technology aspects that are important, as well as some of the policy-related aspects. So, Joe, from your perspective, as one of our lead quantum experts here at Aerospace, what is it about quantum key distribution that's important, and why does it matter that we want to think about this going forward?
Yeah, thank you very much, Lori, and welcome, everybody. Quantum key distribution is important because we're sending more and more devices up into space. And because of that, we have more and more endpoints. And those endpoints want to talk to each other securely, which means we have to have a way of putting up and sustaining more and more keys over a long period of time. The problem with that is that quantum technology itself is being used to attack those keys with Grover's algorithm and Shor's algorithm. And so we have to use the quantum technology, if we can, to distribute those keys so that we can keep pace with these sorts of threats. Space is useful because it's a good way to distribute these keys in free space because there's no vacuum. And on the ground, you have to go through the air or through fiber, and that severely limits the distance over which we can do quantum keying. In space, however, we can tie together ground assets, and we can also key space assets easily. There's 3 different aspects to quantum technology. You can use it to compute, which we're using it for the Grover's and Shor's algorithm. You can use it for communication, which is the quantum keying that we're going to use to overcome that problem. And you can use it for sensing. But we're going to talk about that cryptography issue right now. There's 3 different ways in which quantum keying is important to us. One is the ability to safely rekey things from a distance, whether they're in remote ground stations, such as mountaintops or in the ocean, or whether they're in space. These are places you can't easily walk up to with a thumb drive. There's also the potential to do what's called field boot keying, which is to distribute a key to a device in the field that has no cryptography information. And you may want to do this because you want to throw an asset out there that you don't want to potentially have the key stolen, but later you want to turn it on and distribute keys to it. And then finally, there's one-time pad. And if we can do that, we can have a very, very strong mechanism, but that requires even more keys and longer keys distributed much more quickly. Quantum technology relies on polarization of light to transfer the information. So it turns out that photons have this property called polarization that lets them wiggle up and down, if you will. And we can control that polarization by sending it through what amounts to a picket fence, which is what sunglasses do, or bouncing it off of a surface, which is how road glare happens. We can also measure polarization by sending photons through a crystal. And we're going to use that polarization to encode information. Quantum is this mysterious thing that, Arthur Clarke said that if you properly understand a new technology, it should sound like magic, right? And it does. we've been using quantum technology for over 100 years. Einstein got his first patent, or first Nobel Prize, in fact, for quantum technology. And we are using the three different properties of quantum together. The first property is the idea that information or properties of a device or a particle are quantized. They're in chunks. So you can have 1, 2, or 3 of them, but you can't have 1.5. And that's been used over many, many years now. That's how we have LEDs. That's how we have lasers. That's how we have computers. That's fairly well understood and fairly easy to understand in daily life. But the two other properties that are very magical about quantum technology are superposition and entanglement. Superposition is the idea that a particle can be in more than one state at the same time until you measure it. This is the one that people refer to as Schrodinger's cat, being partly dead, partly alive, and we don't know which one it's in until we open this box and find out. Entanglement is what Einstein called spooky action at a distance. It's the idea that two particles, after they're created and separated by any amount of distance, are intrinsically linked to each other. If you measure one, you know something about the other. So it turns out there's this weirdness in quantum mechanics that normally you'd think if you shine light and put it through a filter, it would reduce the amount of light going through. And that normally is what happens. But there's this weird example where if you have these intermediate filters and you put one in at a diagonal, you actually get more light coming through than you would otherwise. And that's the part that's spooky and weird. So we use that technology and that capability to encode qubits to do QKD. So many people call this the many worlds property of quantum mechanics. You may be familiar with this because it's the one that is predominant in theater and movies and television, Sliders, Stargate, Back to the Future, the Terminator series. They all relied on this idea of many worlds. And that's that entanglement and that superposition we're going to use are relying on that in these stories. In fact, they've actually made it into popular culture. Quantum mechanics and QKD algorithms together are quite complicated and detailed to explain. There's about 10 or 15 different steps. They're shown here. I won't go through them, but what happens is that Alice and Bob, which are the endpoints of a quantum system, want to create a key between them. And they're not going to send a key to each other. What's going to happen is Alice is going to throw things at Bob. That's how we communicate. She's going to throw photons at Bob. Bob's going to catch them. And Alice and Bob are also going to compute some random strings. Okay, they're going to just sort of make them out of thin air or roll dice. The combination of them rolling dice, Alice throwing things at Bob, and then later exchanging things in public, it turns out, lets Alice and Bob both compute the same key. So Alice isn't sending the key to Bob. What makes this magic and what makes it important to us is it is very, very tamper evident. If there's anybody in the middle of that system, we will know, we will detect it. And that's because that randomness and that throwing things back and forth is supposed to have a certain set of statistics when we're done. And if there's anybody in the middle who tries to intercept or even listen in or measure those things, they will collapse that superposition or break that entanglement, those two magic properties that I told you about. And that's how we're going to know somebody's in the middle. That's how quantum keying works. Quantum keying is not tamper-proof. It's not a steel safe. This is sort of like that plastic wrap on a Tylenol bottle that lets you know that somebody's there. And so Alice and Bob can communicate and transfer keys remotely in ways there is no equivalent in classical technology. Okay. But this all comes about in a variety of different ways, and this is new technology, and we're not going to make that happen without policy changes. And Lori, perhaps you could talk about a little bit about that.
Absolutely. Thank you, Joe, for laying out the technological aspects underpinning QKD. And yes, it would be great to talk about policy and what is broadly needed to deploy this new technology. You know, what are the next steps for broader market adoption and penetration? How do we really bring QKD to bear and realize its potential? So to fully mature a QKD market, we need to focus on three key areas. One is partnerships, one is standards and certifications, and one is funding and resources. So we'll lightly step through these three key areas. In terms of partnerships, In 2018, Congress passed the National Quantum Initiative Act, and essentially that did a lot to model the US's role in fostering innovation across public, private, and academic sectors to stimulate that innovation in quantum information science that we really need. The NQI also looked to foster stronger international cooperation that is definitely necessary. And then also, more specifically, we need to make sure that we're engaging with the current leaders in QKD internationally, and these include Japan, Australia, Austria, and the UK. And so those are the important partnership pieces that will help us establish broader QKD market entry. The second key piece is standardization and certification. And really, this is about establishing trusted QKD for that broader application. So we've seen this with every other technology. Trust is a requirement. You need the trust that standards and certification will provide. This will help reduce inaccurate QKD technology claims that might be deterring some potential users, specifically those that are looking to protect high value data, including financial systems, airport traffic control, et cetera. And then standards and certifications also provide definition to what the user might consider buying. And for QKD vendors, it also provides a framework for requirements and how to specify them. So right now, QKD standards and certifications, really, the efforts are in the early growth phase. Early efforts were led starting in 2007 by the European Telecommunications Standards Institute, ETSI, but really, standards only exist at the institutional level, and QKD certification really has not been achieved to the level necessary. And then lastly, or that third prong, is funding and resources. And so the National Quantum Initiative Act that I mentioned earlier was sort of responding to a wake-up call by Congress and the U.S. saying, other leaders and countries around the world are pushing forward, and we need to take more of a focused effort. So the NQI allocated $1.2 billion to the National Science Foundation, NIST, and DOE. Of the $30 million that it allocated to Department of Energy, only $3 million went to fund QKD initiatives. So I'll talk about this a bit later. But one key aspect for the U.S. is that we really are focusing QKD more toward national security initiatives, and it's really government-led, versus other nations are really looking to expand its use in commercial sectors. So that's sort of a difference that we're seeing between the U.S. and other countries. So just let me talk a bit more about some of the current policies, U.S. national policies and guidance around quantum writ large. And some of these have QKD aspects to them also. So I mentioned the National Quantum Initiative Act that had provided that $1.2 billion in funding across a range of government agencies that will flow down to industry as well. Then there's also the National Strategy for Critical and Emerging Technologies that was just released by the White House a few weeks ago, that really focuses on the top 20 technology priorities that the nation should be focusing on. And that includes quantum as one of those. It also includes artificial intelligence, things like that. Another key quantum initiative is the Tokyo Statement on Quantum Cooperation. And this was the first ever bilateral quantum agreement that we've had. And we did that with Japan. So that's something to look to, and potentially, create additional cooperative agreements with other nations. And then in Congress right now is the Quantum Network Infrastructure Act. And this would amend the NQI that I discussed earlier and add about $100 million to the Department of Energy's Office of Science for Quantum Infrastructure to lay infrastructure, develop physical infrastructure for quantum itself. So those are just some of the main technologies, and again, or the policies around technology. So I'm going to kick it back over to Joe for any questions and just for a discussion.
Yeah, Lori, what are the reasons that the United States is so interested in this technology? What's driving this?
So I think a lot of what we're seeing is what you're looking at specifically on a daily basis. There's the national security risks that it could help overcome. The U.S. specifically is focusing more on, the national security applications for this versus the rest of the world, which is looking to better understand how it can be used for financial systems, even, SCADA. And in fact, the current legislation that's in Congress right now that I just mentioned is looking to understand how to apply quantum to the energy grid, and what does that look like? And that's being led by Department of Energy. And again, DOE does get a lot of the funding because they do have 17 national labs that are looking at various types of quantum and what are their applications. So there's a lot going on writ large with quantum, and a lot of funding that's being devoted to it, and also the attention from the White House with this recent the top technology priorities, and sort of trying to focus the efforts around quantum in addition to a lot of other very important technologies.
Right. Yeah, there's an interesting paradox here. A little bit like the internet, QKD is a victim of its own success on one hand, and it's also that very provocative new technology that everybody wants to participate in on the other hand. It's already been used in financial markets terrestrially, and it was actually used in an election in Switzerland a long time ago. And so this technology is commercial. You can buy products that support it. But it's not yet clear whether people who are doing that are doing it because they feel some fundamental need to do QKD, or whether they're doing it for the public relations benefit of being able to say that they're on the cutting edge. The interesting thing for aerospace, I think, is that we're in a different position here. We see that space is a unique enabler for QKD. You cannot tie things together with QKD on the ground beyond about 400 kilometers or so through a fiber, and certainly through the air over much, much shorter distances. Whereas from space, because space only goes through a very, very thin sliver of air as it goes to the ground, you can tie together ground assets and you can tie together space assets almost indefinitely far apart in ways that you can't do any other way. So space is this key enabler to this. We also are starting to see, I think we also have another chart here that explains that there's a lot of different international partnerships that are starting to explore this. I think one of the first ones was China's Mickey's satellite, but Japan has a prototype as well underway in partnership with Canada, and there are other ones around the world where we are trying to keep pace with that. We want to understand the technology, we want to know the technology, and we want to know both the pros and cons, the hazards of it, how to deploy it safely, how to deploy it, and know that it works and trust that it works. And that's always tricky with any new technology.
Yeah. And it's interesting when you walk back the history of QKD development internationally, because really leading it was US, Japan, Canada, Singapore, Europe, way back when. And interestingly, the first QKD network was established in Boston by DARPA. So it, led by the government, in 2003. And then by 2004, it ran between Harvard University, Boston University, a few others. And then between, again, 2008 and 2009, the UK created this QKD backbone in Vienna. And then Japan took lead in demonstrating a QKD network. And now China is really leading, as you mentioned, MISIUS, the space-based validation or application of QKD. They also have a quantum backbone network between, I think, Beijing and Shanghai, leading that to operation into 2017. And then now the U.S. Go ahead.
Oh, I was going to say that the other thing that I find interesting here in terms of the resources that are being allocated, and I think I brought this up in another presentation that I did, is that when you're thinking about the allocations, you're looking at sort of this elephant amount of resources that's being applied towards quantum computing. And that's because people perceive this as being sort of that thing that will crack keys, and that's what we want it for. But quantum computing right now is definitely, I think everyone agrees, in its infancy and only able to tackle very, very, very small problems. It has It's very debatable right now whether it's actually done anything faster than a classical computer. But anyone who has built computers understands that to build a computer beyond any very, very small size, you are building a communication system. You have to have the different parts of the computer communicate with each other. In order for that to happen in a quantum system, in a quantum computer, you have to have quantum networking. We don't know how to do that quite yet. Quantum keying is a step in that direction and also would be able to leverage a quantum network. So the paradox here is, on the one hand, there's a lot of money being invested in quantum computing, but very little in quantum communication and QKD, whereas those are the technologies that will enable quantum computing fundamentally.
Yeah, exactly, Joe. And I think you can even see that disparity in congressional funding and how it's appropriated. So, NIST is working a lot on the quantum computing challenge and opportunities there. And then the Department of Energy is working more, on the quantum communications. And then there's also sensing that we're working on, with NASA and some other government agencies as well. So there's that spectrum. Right. One thing I thought was interesting, and you found this great chart that we can share later, but it's on the number of patents that the U.S. versus China versus South Korea, Japan have for quantum. And it's fascinating to see, the development or the increase. It almost, just shot up within the last year in the number of patents filed, both by the U.S. and China. The other countries around the world kind of stabilized, and we haven't seen much growth there in the last few years. But it was just interesting that there's sort of this, U.S. China, I don't know, race to quantum supremacy. That you can just see by the number of patents being filed. So that's very interesting. We have the hard data there that kind of tells that very interesting story. And it was interesting because.
Yeah, the other thing I found interesting is I think there is a little bit of a correlation between the fascination in the funding world, if you will, of things you can kick and shiny objects. And quantum computers are definitely shiny objects. They are polished brass. Yeah. They have liquid nitrogen flowing over them in pools, and you see clouds billowing out. And they're very intricate. They make good photographs. Okay. Quantum communication doesn't. You can't see the photons flying back and forth. And so it just looks like a rock that's sitting there. So it's not as interesting visually. And the other thing about quantum communication and QKD is, in some sense, it's proving a negative. That's always hard to do and hard to get resources to do.
Yeah.
If you can find a way to crack keys, everyone will know because you've done something. Well, what QKD is trying to do is to prevent somebody from doing something, and that's invisible. That's hard to say, well, okay, I know there's no eavesdropper. Well, bully for you, but I can't see the no eavesdropper, right? It's just this not something there. And so it's very hard to get excited about that when it comes to funding, when it comes to the research, when it comes to the resources, both financial and people, to be interested in doing this sort of work. And so I think that's part of what makes it very, very, very difficult. There is a lot of international cooperation in both quantum computing and quantum communication, QKD. As Lori pointed out, there's a lot of collaborative experiments going on, a lot of collaborative networks, a lot of collaborative satellites going up as well. And there's also a lot of open discussion about the technology, which is appropriate right now with the phase that we're at. There's also a lot of research that has to happen in classified areas, however, in order for us to trust this technology and to have confidence in it, because we're going to use it to make cryptographic keying material. And so that's a whole nother animal. And that's even harder to get resources and people to work on. And so we have this challenge right now. But on the one hand, you can buy products to do this on the ground, and so it's a done deal, and why are we investing in it? And on the other hand, there's this very large mountain to climb, literally, to get this to work in space and to have it be trustable.
Yeah, Joe, I wanted to ask you in a second, so what are future use cases for QKD and also sensing, quantum sensing? But I also want to get back to your previous point you made about sort of how do you justify investment in QKD over other quantum technologies because you can't really see what it's doing. You can't. How do you justify investment in security? And that's a broader problem. I have, and we have working with, government agencies that are working on security issues or securing technology. Because how do you quantify the risk? That is always a hard challenge to do, because you have to be able to quantify the risk to be able to allocate funding to it. So anyway, any thoughts on that? And then also, what are those use cases, in the future for QKD and also quantum sensing?
Sure. Yeah. Thank you, Lori. Yeah. The how to quantify the risk is hard. I mean, it's hard in the classical or conventional sense. And when we come to quantum technologies, it gets even harder. This whole spooky action at a distance is often has this property that you can't even tell whether something has happened until you sort of analyze things after the fact. And so it's important to invest in the technology and to perform the experiments, but it's not like when somebody eavesdrops, right then and there. When you process the data afterwards. That's okay for deploying keys, because what you do is you just don't use the key until you have that measurement, that confidence. But it's not like an alarm goes off or a klaxon sounds when somebody starts eavesdropping. You've got to do some work to find them. And that work, again, is that silent sort of mathematical computation that has to happen. And it's not something you can kick, and it's not shiny, and it's not something you can hold up with a trophy and say, here, I found it. Now, when it comes to the other technologies or other uses of this technology, there are a couple. As you mentioned, you can use this for quantum communication, not just quantum key distribution. Quantum key distribution is a kind of quantum communication that is used to deploy and distribute keying material so that you can both ends compute the same keying material. But you can also use that quantum communication itself in other ways. One interesting property of quantum communication, as I said, is it is tamper evident. Well, that tamper, if you will, is sensing. And so we can use quantum communication to sense things. That spooky action at a distance can tell us when something is there, even when we don't get a photon back and might never have gotten a photon back. So it can be used potentially to detect things that in other ways would be almost impossible to detect. The key thing about quantum technology is it allows us to overcome what's called the Rayleigh limit. When you're dealing with classical systems and classical photons, whether they're radio or whether they're light, you have this problem that you have a limit to how small resolution you can see things, how small a feature you can detect. And it's based on the wavelength of the light or the radio wave that you send at something. And we all know this. Certain kinds of radar can only distinguish things down to a meter. You have to start using other kinds of higher energy things to detect things that are smaller. Photons that are encoded with quantum information can sense things beyond the limit of the wavelength of the photons that we're using. And that's a very, very interesting part of what's going on here. And another part of the work that comes out of QKD. So QKD, if you will, is sort of the standard bearer of quantum communication research. And we're hoping that research in that area and investment in that area and technology standards in that area and trust in that area will help bring quantum communication as a whole forward into the future. That's the hope.
Thank you, Joe. So at Aerospace, we do a lot of work across different types of quantum, with different customers. And so from your perspective, can you give some insight into some of those areas that we're focusing on that you're seeing?
Sure. We're working on a couple different areas. The challenge, as always, is both people and funding resources. That gets harder, it turns out, with quantum computing. The resources that you need to set up a quantum computer can be substantial. We are working on a quantum key distribution experiment right now. I'm actually part of that experiment in the lab, and we're working to downsize it and package it and configure it so that we can make it part of a CubeSat experiment in the future. so that we can gain some experience with it and the different technologies involved and the challenges of doing that implementation. You learn something completely different when you do a complete sort of cradle to grave experiment, as they say, when you're not just focused on, can I throw the qubits from point A to point B, but also, can I compute the endpoints? Can I set up the classical channel? Can I track? Can I do this during daylight with the right filters? Can I get the lasers to work at the same wavelength so that they go through the filters, et cetera? There's a lot of challenges there. We've been working with the different FFRDCs, the partner FFRDCs of ours, and reporting on these sorts of very interesting implementation details that take the experiment from the lab out more to the real world. And I think that's one of the things that Aerospace brings to the table. We also have some substantial work going on in a number of different areas to understand quantum computing, what its capabilities are and what its limitations are, as well as to understand what people call post-quantum cryptography. And I don't like that word. I like the word post-Shor and Grover cryptography, because those are the only two algorithms that we know that a quantum computer can use to weaken cryptography. And so when we're talking about post-quantum, we're really talking about an algorithm that can stand up to or overcome some of the weaknesses that are exposed by Grover's algorithm and Shor's algorithm. And those apply to different kinds of cryptography. And so we are looking at those issues as well to understand sort of what the future brings, both in the quantum world to distribute keys to overcome these challenges, and in the classical world to stand up to the problem of the potential of computers, quantum computers that can crack keys.
Yeah, absolutely. And I think what we've discussed today is that it definitely takes, technological innovation, but also hand in hand with policy to be able to bring about, the results and the work that, Aerospace and a lot of others are doing in quantum. I did have one question about the CubeSat mission. Can you describe a little bit more about that, if it's not a national security issue?
Well, right now our work is what's considered experimental, and it is not only public, but we're doing it in collaboration with international partners around the world. In particular, a company in Singapore we're working with companies in Canada and other places as well. So yeah, we can talk about that. The experiment that we're doing is basically to build a copy of the experiment that was described in the paper that's referred to as BB84, which is after the initials of the two authors, as well as the year it was published, which tells you how long this has been around. Okay, so wow. Quantum keying as a technology, as an algorithm, was proposed in 1984 and then built in the lab about a decade later, and now we're starting to play with it in space. So in the lab at Aerospace, what we're trying to do is to both gain some experience with that and the implementation of the entire system and the integration of the entire system, as well as to understand what it takes to build it with, if we can, as many off-the-shelf parts as possible. So that's the challenge that we've set for ourselves. It reduces costs. It enables us to get things into space much more quickly, because in many cases we're using parts that are already space qualified. And so right now we have an experiment that has been in the lab that we've done some broader sort of outdoor experiments with, that we're now in the process of packaging and sort of miniaturizing. For those of you who know what shrinking dinks are, that's what we're trying to do. Is to make the package smaller, more compact, more efficient for use in a space experiment. And a good estimate of what this might take would be something the size of a fairly thick book. So you're thinking something about 7 or 8 inches on each side and about an inch or two thick. That's the kind of technology we're talking about for the part that's uniquely quantum. You also need a computer. Those can be very small these days, the size of a playing card and maybe 1/4 of an inch thick. But remember, we're sending photons, and anytime you send photons, you need the equivalent of an antenna. For us and for everybody else who does visible length photons, that means a telescope. On a CubeSat, those telescopes can be as small as something the size of a can of soda. But for geographic distances, for geosynchronous orbits rather, those satellites can be very, very big. And so that turns out to be the bulk of the size of the system. But we're already starting to use those sorts of technologies for optical classical communications in space. So the fact that we're now wanting to couple in these quantum experiments to these potentially existing optical links actually might save us some work, so that we don't have to have a separate system. We could sort of piggyback the quantum on top of the classical and put the two together. So that's where we're headed, and that's what we'd like to do. Other parties are working on these similar kinds of experiments with similar kinds of technologies. And they too are using off-the-shelf parts. It's kind of surprising what you can do with stuff that is not very exotic these days. And yet you can do stuff that is quantum. The big challenge for us moving forward, however, is speed. Okay, so there are limits to how fast you can send the qubits, how fast you can generate them, how fast you can receive them safely, and distinguish between different qubits when they're being received. And that's the problem right now. Even though a lot of experiments have shown that you can do the generation of qubits upwards of 10 or even 100 megaqubits per second, the effective rate of key generation is as low as 1 bit per second by the time you account for things like atmospheric losses, pointing losses, the losses in the receiver, the errors on the channel, and the processing of the algorithm itself. Quantum keying is not a very efficient algorithm. In a typical classical algorithm, when you send information at a certain rate, you might have anywhere between a fraction of a percent and 2 or 3% overhead. Quantum keying, the overhead, the intentional loss, and we know it's there and it's not going to be removable, is somewhere in the order of 75 to 80%. And that's before you start talking about these atmospheric effects and these other pointing effects. So that's the challenge for us, is how do you make that system work faster? Because keying at 1 bit a second is just not very interesting, especially if you think about it for low Earth orbit, when your pass contact length is about 10 or 15 minutes. That would be a very small number of bits, 600, 700 bit keys generated in that period of time. And we want to be able to generate keys much more quickly.
Joe, thank you. That was a great sort of send-off or projection for the future, current challenges, and sort of, what do we need to prepare for and overcome relative to next steps with QKD. So just from my perspective in terms of policy, just wanted to summarize. So really for QKD, really need to think about, those 3 prongs of priority areas, focusing on partnerships, standardization, certification, and policy, and funding and resources, really. So that we ensure that, for the U.S., we can ensure that QKD has this technology maturity, accreditation, and standardization, and that we're able to continue this advancement, in innovating around QKD and more widely adopt and deploy. So thank you, Joe. Did you have any final words?
Yeah, just want to add one other thing. As you mentioned, this challenge of the policy issue, the challenge of the standardization, the challenge of trust. These are all huge hurdles. They would be huge hurdles for any new technology. And I think the fact that this is magic and spooky makes it even harder, because the number of people who can explain it, the number of people who understand it, is even fewer. By its very nature. And that's the challenge to us, is to be able to help people understand what this means, why it's important, and how to adapt and to leverage the policies that we have into the policies that we need.
Excellent. Thank you very much.
Yep, thank you all.
A huge thank you to Lori and Joe for that great overview of space QKD and policy. And thank you so much to our production team, James Liggins and Sarah Panoni, located in the LA area. As always, check us out on Twitter, # the Space Policy Show. And you can chat with us on Vimeo using the dialog box below the video. You can also sign up for the latest news alerts at aerospace.org/policy. Our next episode is on the Space Agenda 2021, which you've heard me plug before. It's a series of discussion papers that highlights issues that are likely to emerge in the next few years. And until next time, take care.